Okay, so right now I'm going to explain how to do number 12 in the book on chapter 6.2. And the first thing I'd like to show before I start is um, some tool that I'm going to use on this that is good to know. So normally we see functions as f of x equal to some equation with respect to x. So for example, we can have something like x squared plus 2. But in linear programming, we usually have more than one variable. For this class, you're usually going to have two variables and no more than two variables, sometimes even one variable, but that doesn't really make sense. So usually you're going to have two variables. And the way you're going to see these two variables is as y and x, but they could be different variables. Sometimes, whenever they want you to maximize or minimize a function, they'll give it to you in some form like this, like p equals some x plus some y. It could be x minus y. It could be 2x plus 2y. But the point is, you have two variables that you get to pick and play around with. So there are two numbers that change that are independent of each other. The reason why that's important is because now this is no longer a function of one variable, but this is a function of two variables. This would be written just like you would a normal function, but you would just have two variables. And how this would work is um, if in this first function that I give, if I ask you what f of 2 is, then all you do is plug in 2 for x. So you get 2 squared plus 2. However, in this bottom function, if I ask you what, I can't ask you what f of 2 is because I have two variables. So I have to specify both variables. But if I ask you what like f of 2, like 2, 4 is, then all you do is plug in 2 for x and 4 for y, respectively, because that's the format I have it in. And that would be equal to 2 times 2, because I'd plug in 2 for x, and then I will add 4 for y, because I similarly plug in 4 for y. And seems like an abstract concept, but the reason why we're doing this is because it's going to make it conceptually easier to understand how to maximize and minimize functions. Um, so now that you know how functions of multiple variables work, I can explain to you how to solve this problem. And although this is not necessary for this problem, you could have more than two variables. You could have x, y, z, w, and an infinite amount of variables, as long as whenever I specify the equation, it has those variables. Um, and then all I have to do is specify how I want to plug them in. But if that doesn't make sense, just don't worry about it, ignore it. But it's good to keep in mind. However, for this problem, we're only going to focus on this. Um, so now let's start with, in problem 12, uh, isolating the equations for y. Because before we start graphing these equations, although one thing that people like to do, and I know Grant likes to do this, is just figure out the x and y intercepts and then graph the equations. I personally like isolating the equation for y. What I mean by this is on the subject to equations, we have, for the first one, x plus y is greater than or equal to 2. So before I graph this, what I like to do is get y by itself. So I get something like y is greater than or equal to 2 minus x. The way I got this is by subtracting x from both sides of the equation. So the way I graph this is I say, okay, well, this is just an equation with a y-intercept of 2. So it has a y-intercept of 2, and it has a slope of negative x. So it looks something like this. It says the slope of negative x, it goes down 1. So it goes down 1 to the right 1, and then down 1 to the right 1, and then it intercepts there. But you can just graph it as if it was a normal line. And I will make it a solid line because there's an equal to sign here. If there was not an equal to sign there, if it was just greater than, then it would just be a dotted line. That's the only difference. And now I can shade my feasible region by, or sorry, that's, yeah, so I would shade my feasible region by just highlighting whatever's on top of x, of y, or the equation. So this is the equation, and then I would want to shade what's on top of it. So this area on top of here is our current feasible region. And it goes on forever so far. And the reason why is because we really got, we're keeping these y's and everything on top of it, everything that's greater than that y. That's what that greater than symbol tells us. And we can do this for each equation, isolating for y. So for example, for the second equation, and the subject to is x minus y is greater than or equal to -2. So for this one, we can add y to both sides because we want the positive y, and we get x is greater than or equal to -2 plus y. Then we add 2 to both sides to get rid of the -2, and we get x plus 2 is greater than or equal to y, which can be rewritten as y is less than or equal to x plus 2. And likewise, we can graph this by saying, oh, y-intercept of 2, and it goes on, let me draw this, y-intercept of 2, and it has a positive x, so it just goes on like this forever. And I'm going to shade the area under that curve because it's a less than symbol. And keep in mind, notice how I did a solid line there because, again, we have the equal to sign right there. It's good to keep in mind if we did not have that, we'd have to do a dotted line like this. But in this case, we have equal to's, so that's good. So the way we're going to graph this is by just shading in the area under that. And it's honestly all this area, including what's under here, but we're going to ignore that because we can't have any area under here. So you see how the area right here is it's interlapping with both of these equations. That's called our feasible region. The area that's interlapped, like the area interlapped by all of the equations. So to be more specific, let me draw it in a better graph here. I have all the equations isolated for y. There's 3 of them. And then I'll explain what happens with x is less than or equal to 10 and y is less than or equal to 10, and how that works. So for the sake of this, let's draw the first equation. So I'm going to draw that in yellow, so the lines are corresponding to each other. And I'm going to draw all the lines first and then shade in the right areas. So we have a y-intercept of 2 and a slope of -x. So it looks something like this. It goes on forever. And then I'm not going to shade in the correct area yet. I'm just going to draw the lines. But then I'm going to draw the pink line, and that's going to be y is greater than or equal to x minus 2. So that means we have a y-intercept of -2, and then we go up a positive x as our slope. So we're going to do that. And then we have y is less than or equal to x plus 2. So again, we have a y-intercept of 2. And we go on graphing this as a straight line going like this because it has a slope of 1. So let me just graph that. It goes on forever. So now we can graph the areas that interlap for these. So for the yellow one, it's going to be everything on top of the line because it's a greater than symbol. We can see that right here. So I'm going to shade everything on top of the line slightly. So it's something like this. And then it does go on forever. Keep that in mind. And then for the pink line, we shade everything. Well, the pink line, well, the first pink line we drew, which was the bottom. There's this first pink line. So corresponding to this one. So the pink equation, we're going to shade everything on top. So that's going to be all of this area. And, it goes on forever also. And it's starting to look messy, and that's kind of the problem with linear programming. But, we can now shade the area under this curve, which is this curve right here. So the area under that curve can be shaded as this right here. And it looks really funky. This looks like I just scribbled everywhere. I understand. So, let's make this look better. Let's find out what area is overlapping in all of these. And clearly, it's this area right here, this little area right here. and then everything that goes on top of that. So if I were to go on forever, I could keep shading in this area because these lines keep going on forever. And to make you visualize it a little better, I'm going to erase all the other lines. So our feasible region is that black area right there, because that's the area that overlaps all the equations. So let me just draw that again. And it goes on forever. You have to keep that in mind visually. Sometimes what some professors and books like to do, which I'm not a fan of, is drawing a rectangle where they imagine an invisible rectangle right here, and they just imagine that there is a coordinate right here. The reason why they do that is so they can visualize what's going on. But I believe that the students taking this class are pretty smart, and they can imagine that this line goes on forever. So if you can imagine that this goes on forever, you can always plug bigger and bigger points that are in that feasible region. You don't need to draw the rectangle. I believe most professors actually don't really care about the rectangle. They don't actually draw it. As long as you can get your answer, it doesn't matter. And if we just had these equations and I asked you to minimize this, then what you have to do is figure out your corner points, which are found by the times that the line gets intersected, which would be this point right here, which is 0, 2. This point right here, which is 2, 0. And those are our two corner points. However, you got to keep in mind that this goes on forever. So we should plug in a point, that's somewhere in that feasible region, so we know how big that would be. So let's pick like a point over here that's really, really big. But we have to make sure it's part of the feasible region. And I can pick a point that I know will work, called, let's just choose something like, let's see, 1,000, 1,000. Actually, that's too much of a big number. I don't want to do the math. So let's do 12 and 12. The reason why I picked that is that point is somewhere right around here. So it's still in the feasible region. And it should give me a good estimate of what happens when I plug in a big number in that feasible region. If I were to do that, then, you can plug them into this equation right here that we're trying to maximize and minimize. And if we're trying to minimize, we're going to find out that, you can plug it in yourself and figure it out, but you're going to find out that the smallest corner point, the corner point that will yield the smallest value for P will be the one with the bigger Y, this one. The reason why is because if I do that point, I'm going to have 0 for 2 times 0, and then I'm going to subtract 2. So my final answer is going to be -2. So it's going to yield a P equals -2, which is a small number. But if we try to do the same thing for the point 20, then we're going to get 2 times 2, which is 4, and then -0. So this is going to give us P equals 4, and clearly that's bigger. However, when we plug in 12 and 12, we're going to get 12 times 2, which is 24, minus 12, so it's going to give us 12. So this weird point over here is going to give us 12. And if we plugged in a bigger number, like 1,000 and 1,000, we get 1,000. The point is, this is a bigger number than this P equals 4. So what we can tell here is that if we're trying to minimize this equation, then the smallest corner point is going to be 0, 2. This combination of X and Y will give us the smallest p-value no matter what. And it doesn't matter that it's unbounded in that case, because if we plug in a big number like 1,000, 1,000, or 12, 12 in this case, it's just going to give us like a bigger p-value, which is it's bigger than the one we found for 0, 2. And since we're trying to minimize, it doesn't matter to us that we can get bigger values. However, on the other side of the spectrum, if we're trying to maximize, it's the exact opposite. We actually have a scenario that's unbounded. And this is where you put in your answer that the equation is unbounded. And this is where it's important, because now we're saying, hey, we cannot find out what the max combination of X and Y, what combination of X and Y will give us the maximum p-value, because we can always plug in bigger values that are in this feasible region and get bigger value for P. For example, I plugged in 12 here and I got 12, 12, and I got 12 for P. If I plugged in 1,000, 1,000, I get 1,000. And clearly that goes on forever. I could plug in a million, and get P equals 1,000,000. So this is an area where we're unbounded. So if you were asked a question about this problem, and you don't have this right here, like the x is less than or equal to 10 and the y is less than or equal to 10, then we'd say that our minimum value for our minimum value is occurs, the minimum value for p, our minimum p occurs when minimum p is when x is equal to 0 and y is equal to 2. The reason why is because it corresponds with this point. But we would have to say, if we're trying to maximize, that this is unbounded. So max p would be unbounded, is unbounded. The reason why is because we don't know what max p is, and it has no bound, it has no limit. P can be maximized indefinitely. We don't really have a max value for p. So that's where you'd say that the max p is unbounded. And I know this is a lot of information, but my goal is that you can slow it down, you can go back, try to understand it. But this will help you understand most linear programming problems. But this is how this would be affected. Now I'm going to bring in, we got to keep in mind that for this problem, number 12, this is not the answer. The reason why is because we do have another constraint, and that is that x and y are less than or equal to 10. And this is why they matter, because our answer here for our minimum is not going to change, because that's our minimum no matter what. But when we add x is less than or equal to 10, we say, hey, let's add a line right here, and let's shade in the left side. And now let's add a line up here, and let's shade in what's under it, right? Y is less than or equal to 10. So now we have a different constraint, because now it's no longer unbounded. Now we closed it up. We kind of we set a limit to it. We have this line right here, and we're setting a limit to it. Now we only have, for our shaded region, this area right here, but it stops at this corner, right? And this right here is the point where x is less than or equal to 10 and y is less than or equal to 10 meet. So this is the point 10, 10. So we can get rid of this right here. This is the point 10, 10. This right here would be the point. Let's see. This would be, so y is 10 and x would be, so this would be the second line. Let me just do some math real quick. If you drew a better graph, it would probably be 4, but let me just make sure. So, because it may be wrong. It should be a different number. Because my thing's not drawn to scale. So that's this line right here. Let's see, it's this line right here. So it would be, x should be, if I'm correct, 8. So it should be the point 8, 10, and yeah, and this point is still 2, 0, and 0, 6. So now we have a very bounded system that is really easy to figure out, because now we don't have anything unbounded, so we can just plug in all our corner points and figure out the smallest p-value and the greatest p-value. So now we can find out p for this corner point and p for this corner point. So if we plug in 8 for x, then we get 16, and then we subtract 10. So this would give us p equals 6. And then this 10, 10 would give us p equals, well, we plug in 10, we get 20, subtract 10, we get 10. So that's plugging it into this equation. So clearly, our smallest p is still the 0.02. So our minimum does not change. Notice how that happened. Nothing really happened with that when we added the two constraints of x is less than or equal to 10 and y is less than or equal to 10. However, notice that now our answer for the maximum is no longer unbounded. Now the answer for the maximum is 10, 10. The reason why is because that gives us the biggest p-value. And there's no other point bigger than that will give us a bigger p-value, because now we can't plug in 12, 12 like we did previously. So now our answer would be that the max p occurs, you can say this however you want, or you can say when x equals 10 and y equals 10. And you obviously would use more English. You'd say, the max p would occur whenever x is equal to 10 and y is equal to 10. Or y is equal to 10 and x equal to 10 yields the greatest p-value. You get the point. But the reason why I explained earlier that you want to write it in this format, not just p equals, is because if you wanted to check your work with an online calculator such as Desmos, this would come in handy, because you can write it in that format and figure out your answer. So let me show you what I mean. Let me share my screen with Desmos real quick and show you. So let me share my screen real quick. And let's see. So let's have these graphs. I think I kind of have it here already, but let me make sure it's correct. X is less than y is greater than equal to 2. X minus y. Okay. All right, seems correct. Okay, so now we can graph the first line like we did earlier. And this is weird. Did I do something wrong here? Let me make sure. Oh, no, this is just a line that has a slope at -2, and then it goes down. And this is the first line we drew. And then when we draw the second line, now we have a constraint because now our feasible region is only the area that interlaps. So right now it's only this area right here. But now we're going to add another equation. So let's add the third equation, and you notice how now this is the scenario we had earlier. Well, we haven't added x is less than or equal to 10 and y is less than or equal to 10 yet, and our feasible region is this right here. And there is a limit to how small it can be, but there's no limit to how big it can be. Let me show you what I mean. If I decided to zoom this out, you can tell, this I can plug in really big values right here. If I go to these points right here, it's like hundreds, and it just goes on forever because they interlap forever. However, the point of having x is less than or equal to 10 and y is less than or equal to 10 is that I can set a limit to this. So let me show you what I mean. If we were to graph x is less than or equal to 10 and y is less than or equal to 10, now the interlapping region, whenever we have x is less than or equal to 10, is this area right here still, but it gets capped out when it reaches that line. And likewise, when we do y is less than or equal to 10, it's going to get rid of some of the roof. We're going to kind of shave off the hair right there. So, we're only going to have this region right here. We're going to have more corner points, right? So that kind of makes sense. We can find out all those corner points right here. So I can just click on them and find out what they are. I would like doing this by hand first, so I kind of know what I'm doing, because this can be overwhelming with so many points. But those are all my corner points. So now the reason why I taught you the multiple variables thing is because if you write it in this format, since this is a computer, we can just put in, hey, find the value of P of, let's say P of 10, 10, because that's one of the points. P of 10, 10, 10 for x and 10 for y. That gives me P equals 10. So now let's try a different corner point. Let's try this one, which is A10. So P of A10. See what that gives me. And that gives me 6, like we found out earlier. I think I forgot to draw this point, but it shouldn't matter. This will give me P of 10, 8, which, we'll find out another point right here. But that'll give me 12. So you see, actually, good thing I checked my work, because I would have been incorrect. Even me as a mathematician, I make mistakes. So I was incorrect. The maximum value occurs when x equals 10 and y equals 8, because it's actually greater than what I originally thought. So that's because I missed one of these points because I was graphing it by hand. So this is kind of good to use technology sometimes to check your work. So anyways, let's keep drawing these. So let's see, P20 and P02. The one that was minimum, I think. Yep, -2. You see, it kind of give us what I wanted. Let me stop all this mess that we drew. But now we see all our values plugged in. So now we got to identify which is the greatest value. Well, clearly it's 12. It's the greatest value is 12 when when we plug in 10 for x and 8 for y. So we would say that the maximum value occurs when x is equal to 10 and y is equal to 8. And that value would be 12. So the maximum value would be 12 at that point. Originally, we said it was 10 and 10, but that's because I missed the point 10, 8. And you may have caught it when you saw me do it. But, it's good that we checked the Desmos, because that showed me that was the wrong answer. And it's actually the point 10, 8. And the minimum value occurs at -2. It occurs when P equals -2, which is when x equals 0 and y equals 2. So, you can say all that stuff. So, to kind of summarize, you want to always isolate for y first on your subject to, so not on your maximized equation, because your maximized equation is what you're trying to plug in your corner points at the end. But the first thing you want to do is isolate your equations for y, and then graph them all, find out your feasible region, which is when this all intersects. And sometimes they won't intersect. And if that happens, you'd say there's no feasible region. But the first thing you want to do is isolate for y, then graph. And then you want to identify, is it unbounded or not? In this scenario, it would be unbounded, but if we x is less than or equal to 10 and y is less than or equal to 10, then it's no longer unbounded. So, it's not going to be unbounded for a minimum or maximum, so that means that it's bounded both everywhere. There's corner points everywhere, it can't go on forever on either side. So here you would not worry about unbounded. You would never actually draw rectangles or anything if you do that method or if your teacher teaches that method. So that's how you know when to use rectangles. If your teacher teaches that, you know how to use rectangles whenever it's unbounded. When it's not unbounded, you don't worry about rectangles. When it's unbounded, you use a rectangle so that you can figure out some obscure value that's, up there. And, that's the first step is graphing it, then figuring out the corner points, and then, plugging all those corner points into your objective function, which is this p of x, y, and figuring out which one gives you the greatest value and the smallest value. If you get a value, so this is a cool thing to realize. If your graph goes on forever in one direction, so for example, we don't have this, the x is greater than or equal to, or less than or equal to 10 and y is less than or equal to 10, then it goes on forever in this direction. That's one direction. So something we're going to note is that either a maximization or a minimization is going to be unbounded, because one way or another, we can go on forever. However, the other one will be bounded. However, if we have two things that are unbounded, so for example, if it's unbounded in both directions, so for example, if I get rid of another one here, like this one, then in this case, both minimizations and maximizations will be unbounded because it's unbounded in both directions. However, keep in mind that sometimes you will be asked to only maximize or minimize, and you'll have to figure out whether it's unbounded or not, and then figure out if it even matters that it's unbounded or not. You can use a rectangle or not. I personally don't like using it. I just like thinking of a big value that's in the feasible region. But once you plug in those values, you figure out which one gives you the biggest or smallest p, and then those are your 2 points. That's your point. So your combination of x and y that yields the greatest or smallest p value depending on what you're trying to do. And I would say that is how you do this problem, and checking with Desmos is always good, as you saw in here. And I think that's practically everything. But if you have to go back through this video and rewatch it, feel free. And I would say that I covered more than I needed to for this problem, but my idea was to cover everything you'll see in linear programming, because this video could be one that you use as a resource for more than just this problem. You could use it for whenever you're doing other problems. I mean, I covered the fact that, a graph may be unfeasible, so meaning there's no feasible region because they don't interlap. There may be a graph that's bounded in all directions, unbounded in one direction, or unbounded in both directions. So the idea is that what I covered in this video, although it seems like a lot, if you get this correctly, there's no problem in 6.2 that you should not be able to solve. You should be able to solve almost every single problem on 6.2. Except maybe, the application problems can be hard, but you should still have the tools to solve them. So treat this more like as a lecture. The fact that it's less than 40 minutes is better than some teachers can do, but go at your own pace, pause it, speed me up if I'm too slow. But yeah, just keep in mind, if you make mistakes, we're all human. Everybody makes mistakes. I study mathematics, and you saw me make a mistake here where I found the wrong answer until I checked with Desmos. So, this is all there is to linear programming, and I hope it's not too scary. Math can be fun sometimes, but yeah, I hope this helped.